Hello everyone, I'm Siddharthan. This is the 21st machine learning project in our YouTube channel, and in this video let's understand how we can build an autism prediction system using machine learning. So we will start with understanding the dataset that's present in Kaggle and then work on steps such as exploratory data analysis, data visualizations, data pre-processing, and also do the model training along with hyperparameter tuning, model selection, and so on. So this particular use case will cover almost all the things that we would do in a typical machine learning use case. So before getting into the coding aspects, let's just go through the workflow that we are going to follow and basically what are all the steps that we will be doing. So the first part is data collection. As I said, this is a Kaggle dataset, but in real time, right, or in real world use cases, we often get a particular dataset from a client, or we would probably like collect the data ourselves, and in most cases it would be present in a data set and you have to write some queries in order to get this. Whereas in the case of Kaggle, we can just directly download the CSV or the Excel file. So in this case we are going to directly work on the CSV files. So that's the first data collection part, and then we also do some initial investigation on this particular data set. So the next step is EDA, or exploratory data analysis, where we are going to understand about this data, and this is a very key aspect because doing this will also help us to make better decision on the models that we are going to use, and basically what are all the different data pre-processing steps that we have to do. So let's say there is a class imbalance in a data set which we will face in this particular use case, so that can be identified during this exploratory data analysis. If we kind of don't do this right, so we may kind of miss some of those key things that we need to handle. So after data collection and data loading, so we will work on the exploratory data analysis as well as the data visualization. So once that's done, based on the insights we would get and based on the usual things that we would do, we would perform data pre-processing, where we would work on, let's say, identifying the outliers, handling that. If there are any missing values, we would handle that, and let's say there is a class imbalance, so we would take care of that and so on. And then we would do a train test split, where we will split the data set into training data and test data, where the training data would be used for training the model and the test data is used for evaluating the model, which is pretty basic stuff, and I hope that everyone knows this by now. And the next step is working with the ML models. So in this case, we will be working with three tree-based models. So we will have decision tree, random forest classifier, and then XG boost classifier, XGB classifier. And we will try to do this hyperparameter tuning as well as model selection to understand which of these three models would be the ideal model in this particular use case, and also which set of parameters are the best hyperparameters that we can work with. So you would have the best trained model out of this particular three models and the different variations that you're trying. And once that's done, we can build a predictive system that can predict the labels. So this particular part of building the predictive system, I want to leave it to it, or basically give it as an exercise so that you can try something on it. So this is this entire thing that we can follow. So of course, you can also try different models like logistic regression or support vector machines as well. So here I've taken tree-based models, but even you can explore other models as well. So this is the workflow that we are going to follow, and let's get started. So I'm going to work on Google Collaboratory. You can work on Google Colab or Jupyter Notebook, or even VS Code supports Notebook. So for this particular use case, notebooks are a better option, as we have several that we have to do, and basically notebooks are better for exploration and do a lot of analysis compared to a IDE, just for this particular like use case. When you're like working for the first time on a data set, when you want to analyze few stuff, then in that case notebooks are kind of like preferable. So for this, like, we can just work with the CPU environment itself. So I've just like logged into my Google Collaboratory and just created a notebook called as Autism Prediction using machine learning. So I'm going to connect to it. And the other advantage is that we can also always like kind of ask some question to Gemini if we want. So we'll maybe try to use it whenever we want. So that's like another advantage. We can just quickly look into it. So the system is connecting. In the meantime, I'm going to create a text cell and call this as importing the dependencies. Okay, so let's maybe make this in bold. So this is the first step that we will be following. So here let's import all the functions and the libraries that we are going to need. So the first library I'm going to import is NumPy. So import NumPy as MP, which we may use a bit later. And then of course we need pandas, as we need to load this CSV into a pandas data frame. So that is the next step. And then I'm going to import two visualization libraries. One is matplotlib. So I'll import matplotlib dot pyplot as plt. So this is the matplot library, and I'm also going to import cborn as SNS, as this can be used for some styling for our plots. And then I'm going to import from scikit-learn dot preprocessing, import label encoder. So L and E should be in caps. And next thing is from implearn dot oversampling, import smooth. So this particular dataset has some class imbalance. I'll show that to you in Kaggle in a minute, the autism prediction dataset after importing these libraries. So here we need smooth, which is synthetic minority oversampling technique. It's basically like when you have imbalance class distribution, we can perform oversampling using this smooth method, and for that we can use this IMB learn library. And then from sklearn dot model selection, import train test split, and we will also import cross-vals code to perform cross validation. And as I said, we will also be doing hyperparameter tuning, and these are tree based models, and we are testing for three different models, right? So grid search CV may take like a very long time, so I'm just going with randomized search CV so that it basically takes lesser time for that particular distribution of hyperparameters. So I'll just go with randomized search CV, but you can definitely try hyperparameter tuning with grid search CV as well. And then I'll import the models that I need. So I'll import from sklearn dot tree, import decision tree classifier. So this is a classification problem where we are going to say whether a person has this autism disorder or not. And the next model that we are going to import is from sklearn dot ensemble. So the ensemble model that we are going to use is random forest classifier. And the third model, the third tree based model that we will be using is uh, from XGBoost. Import XGB classifier, and then I'll import from sklearn dot metrics, import accuracy score, confusion matrix, and classification report. So let's import these three things to get like a well-rounded performance metrics. And finally, I'll import pickle in order to save our model. So these are the libraries that we need. So first we have NumPy, which we may use in some cases, some basic stuff from NumPy. So we still don't know why we are going to use it, but it may have some uses later on. And then we have pandas, and we are importing this pandas as PD, which is mainly used to read our CSV file into a pandas data frame and do some processing on it, and also do some analysis on the data frame. And then we have matplotlib and cborn basically for our data visualization plots. And then from sklearn.preprocessing, we have imported this label encoder to work with the categorical features that we have in our dataset. And then we have imported smart in order to handle the class imbalance that we would see in this particular dataset. And then from sklearn.model selection, we have imported train test split, cross val score, and randomized search CV. So this is for splitting the data into training data and test data. So this is, instead of just relying on one accuracy score, we would do a cross validation on, let's say, 5 different floats, and try to get a more reliable accuracy score. And then we have randomized search CV to perform hyperparameter tuning on the three different models that we are working on, which are the decision tree classifier, random forest classifier, and XGBoost classifier. And finally, we have the sklearn metrics such as accuracy score, confusion matrix, and classification report. And finally, we have imported pickle, which will be used to save our model as a file. So these are the libraries that we will be working on. So now let's go to Kaggle. You can just search for this autism prediction in Google. So it should kind of get you there. So just search autism prediction Kaggle. So this is the dataset that we will be using. And if you want to download this dataset, right? So first you need to accept the competition rule. So make sure that you have an account in Kaggle, and then you can go to this rules. Here you would have an option to accept the competition rules. Later you would be able to download this dataset. If you don't accept the rules, you won't be able to download this. So here we have this sample submission, train, and test. So we will be working on this train dataset alone, because for test we don't have the labels. So this is when you are kind of submitting for Kaggle competition, you will predict for this test dataset. But for us, for learning purposes, we can just use or basically work with this train.csv, and here you can download download this. You can select this train.csv. You can download this from here. So this will download this train.csv file, to your PC, or you can download this entire data. So that entire thing will be downloaded as a zip file, and then you can like kind of work on it. So that's the process. So here you can see this train.csv is downloaded. So I'll come back to my code. You can also spend some time to understand the different columns that we have. So here we have the ID of the patient column. So this ID is just some serial number, right? So this won't probably have like some influence on the target variable that we have. And then we have A1 score to A10 scores. So scores based on autism spectrum quotient item screening tool. So let's say that there is some screening process, and based on that they are kind of finding these scores from A1 to A10, and like all these are mainly like binary values. So you either have 0 or 1 in these values from A1 to A10. And apart from this, we have this age of the patient in years, gender, male or female, and then we have ethnicity, like what's their ethnicity or race, and then we have jaundice, whether the patient had jaundice at the time of birth. And then we have so this is also like a categorical column, so you can even scroll here and look at it. So in this you can maybe ask it to show all the columns, so that will display the sample of all the columns over here. So after A10 we have the age of the person. The age is in floats, maybe we can work on it later. So we have male and female. Female has only like 34 percentage and male has like 66 percentage. And then you have ethnicity, so white, European, and so on. And then you have jaundice, yes or no values, and then autism. So this autism is nothing but whether an immediate family member, let's say a brother or mother, or a father, has like autism, right? So it's that particular categorical variable. So this is not the target variable. So this is like kind of the patient history that we have over here. So it says whether yes or no. And then we have country of residence, or country of residence of the patient, so where currently the patient is residing. So that's another column. And then we have used up before, whether the patient has undergone a screening test before. So we have again that as an yes or no value. And then we have result, some numbers that, and it's score for AQ to A10 screening test. So we have the result for all those values. And then we have age of the patient. Not sure what is this age, DESE, but in this particular column, right? So all the values are this thing 18 and more. So there is like only one unique value. So when a particular column is there and it has only the same value throughout uh, the rows, right? So if we just have like one unique values, then it doesn't have any influence on the target variable, because it's not changing, right? So no matter what the value here, it's always going to be the same. So you can directly remove this column, as this is only one unique value. Let's discuss this later, but that's about this age DESE column. And then we have this relation. So it basically tells whether the patient is 18 or more. So yeah. And then you have relation of patient who completed the test, so who basically returned the test. So we have self and others and so on. So we have some categories over there which we will work on later. And finally we have our target column, which is class ASD. So classified results as 0 or 1. So here 0 represents no, that means 0 means the patient doesn't have autism, and 1 represents yes, that means they have autism. So this is the target column, and during submission submit the values. This is something that we don't need. So the main thing is the two class values are given as 0 and 1. So 0 means autism, and sorry, 0 means there is no autism. 1 means the patient has autism. So if you just search for this ASD full form, right? So it means autism spectrum disorder. So that's what we are classifying in this particular data set. So we have already downloaded this train.csv. So now I'm going to upload this over here. So I'll come to this files thing and click on this upload button. And I have this file in my desktop, train.csv. So this is that autism dataset that we have downloaded. So I have another copy over here. So this is like a very small data set. It's like 77 kilobytes, so it shouldn't take a very long time. So we have already imported the libraries. So now we can work on, you know, loading the data set and just doing some basic inspection and getting a basic understanding of the data set. So I'll number this as two. So the first step is importing the data set, and the second step is data loading and understanding. So I'll make this in bold. Okay. So now what we are going to do is read this CSV file into a pandas data frame. So we often work with CSV files, or as well like you also work with Excel files. So if you are using Excel files, you can use read Excel function. For CSVs, you can use read CSV function. So this is read the CSV data. to a pandas data frame. So CSV is nothing but comma separated values. So all the values are separated by comma in that data set. So I'll name this data frame as df, short form for data frame, and say pd.read csv. So pd is the pandas that we have imported over here, and within this I'm going to read the file, and the file name is train.csv. So you can just mention train.csv because both the file, this notebook and this train.csv, is in the same directory. Or if you just want to be very clear, you can just go to this train.csv, click on this option, copy the path, and paste this entire path of the file over here, so that you don't have to worry about that relative path of dataset and the notebook. So it says content train.csv, and run this. So now we can just do some initial inspections. I'll just maybe mention this over here. Initial inspection. And it's basically like understanding how many rows that you have in a data set, like the sample of the data set by running dataframe.data and so on. So first I'll run df.shape. That's going to give you the total number of rows and the columns that you have in your data set. So you have 800 rows in your data frame and 22 columns. And then I'll do this df.get, and that's going to give me the first 5 rows in my data frame. So we have id column, which as I said, it's not useful for our modeling, as this won't have any influence on the target variable. And then we have a1 score, a2 score, all the way up to a10 score, which are binary values. We will also verify this later. And then we have age of the person, which is in float, which is not ideal, so we can maybe convert this to integers. And then we have gender, ethnicity, jaundice, uh, whether they have jaundice on birth, so which we have seen. And then we have family, close immediate family members have had autism or not, country of residence used abuse. So we have all these things basically, right? This is something. And then you can also print the last 5 rows of a data frame by running df.tail. So that's going to give you the last 5 rows of this data frame. So if you see this here, right, so in the ethnicity column, and there is also this relation column that would have this question mark, which are basically missing values. We will look into it later, but just going through this will help us identify that there are some issues in the data set that we have to work on. So these are just like basic inspection that we are doing. And at this point, I just wanted to mention another thing. So sometimes in the number of columns in your data frame is very large, right? So it kind of will be truncated. You won't see all the columns. In this case, you're able to see all the columns, but again, it would be like truncated in some cases when the number of columns is more. In order to avoid that, right, to display all the columns of a data frame, whenever you are doing this data.8. Basically, like whenever you're printing a part of the data frame or this entire data frame, if you want all these columns to be present, you can use this set option thing. So you can say pd.set option display.max columns command n. So we are setting this option called as display.max columns none. So when you do this, no matter how many columns that you have in your data frame, so all those columns will be represented here, so it won't be truncated. In this case also it's not truncated, but this would probably be helpful for you in some other cases. So I just wanted to mention this thing. So when you run this, you have to run this like only once. After that, it would automatically be displayed, like wherever you're printing this data frame, all the columns will be displayed. So that's the other thing. So we have printed the sample of this data frame, first 5 rows and the first 10 rows, and we could visually see like some issues over here. And in the next step, let's do this df.info. So that's going to give you the information about this data set, such as the data type of the columns, whether there are any missing values, and so on. So we have 800 entries, that means 800 rows. So the index would start from 0 to 799. So 0, 1, 2, all the way up to 799. So that would contribute to 800 rows. And then you have column id, a1 to a2 score. So all these columns are there. And non-null count. So null values means the values that are missing. Non-null values means like those values are present. So out of this 800, all these 800 values are present. So for this id column, it is an integer data type, integer, 64-bit integer. A2 score is also 64 integer, and so on. And some columns are object. So usually the categorical columns are object based. So here you have gender, which is represented as male or female, ethnicity, which is also string. So all these strings are represented as objects in your data type when you run this df.info. Basically this a1 to a10 is also categorical, but they are represented as 0 or 1 as numerical values, so that's why we have integer, whereas the categorical variables with strings are represented as objects. So that's why we are basically working with this label encoded thing. That's another thing to remember. And then we have result as float 64, and interesting thing is age is present as float. So if you want, you can leave it as such, but I want to convert this to an integer so that it's kind of an integer. You can either round these values, or I'm just going to not round these values, just convert these values to integers. So we will come to that. The main problem that I'm seeing over here is, as I said earlier, I've seen this data set before. So this ethnicity as question mark, right? So what they have done is, instead of representing this as NaN or not available, so when the value is NaN or it means not a number, those would count as null values. But in this particular data set, so they don't want to do that, so they have replaced this missing values with question mark. So it's not counting as missing values here, but we could see that there are some values that has question marks, so this will definitely create some issues. And there are some question marks that present in this relation column as well. I'll show you this to you later, but these are some things that we need to remember. The reason people usually do this is like is because sometimes you don't want to have missing values represented as NaN. So what would happen is, right, let's say that there is age column, right? So let's say that we have this age of the person, and there is a missing values in 10 rows out of this 800 rows. When you're putting this in a data frame and when you're saving this, you don't want to leave this as a empty cell or a empty space or with some NaN values. So instead what usually people do is, right, so they can replace the values with something like minus triple nine, minus thousand or something like that. So we know that the age of minus triple nine is not applicable, but that's why people can represent missing values instead of saying NaN, which would count as missing values, which may be not ideal in cases where they are storing it in a data frame, or in some cases they would replace it with these kind of placeholders like minus triple nine and something like that. So that's why I'm seeing this ethnicity as well. So it can be either the person who kind of collected this data was not able to identify their ethnicity, or it's kind of like missing values they want to represent it. So that's why they have this as question marks. There are like some reasons to this, so you need to understand what's there. I mean, like, what's the reason for not having those data, so that you can handle it accordingly. But if we don't have that information, we have to handle it somehow, right? So that's one thing. So this is the main insight that we are getting for now, that some of the columns have this question mark, but they are not counted as NaN values or missing values. That we have to do. And in this first step, as we discussed, I'll just convert this age column that is in the form of float to integer value in a second. So yeah, okay. So I'll come back here. I'm going to convert this age column to integer. Convert age column data type to integer, which is as floating point now. So I'll say df of age. So df is the data frame name and age is the column name. So you can say df of age is equal to df of age, same thing, dot as type int. Okay, so here we are taking this df age. So we are kind of working on this df of age column, and what we are doing here is taking this age column again and converting this data type to as type integer. So this means, like, take this column, and this column is currently floating point. I'm going to convert all this to integer value. So I'll run this. So now you can again perform df dot int, but I don't want to look into like all those 5 rows. So instead I can just say df of it 2. That will just give you the first 2 rows in your data frame. So yeah, so we have this age column, which was previously 38 and 47 is the current value. So previously it was 38.17, 47.7. So we are not rounding this, but we are just like converting this floating point to integer. So that would just remove this decimal values. You can also work on rounding it if you want, like a better representation. So that's completely up to you. So this is the thing. And the next thing that I'm going to do is, mm, take all these values like A1 score, A2 score, or all the columns, and try to find the unique values, because that would tell us like what values are basically uh, you know categorical columns, what values are numerical columns. So if you think about this age and the result columns, right, these two are the only ones that are kind of numerical. So the number of unique values will be more, because the values can be some anywhere between, like, let's say 18 to 60, 70 or something like that. Result is a floating point value. So these two rows or these two columns will have like several unique values. So instead of these 2 rows, we can try to find the unique values of all the other rows and make sure that all these are categorical. And even id, we don't need id at all. So what I'm going to do is, using for loop, I'm going to print the unique values of all these columns except id, age, and result. So you can do this manually, but there are like about 20 columns. I don't want to do this for 20 columns manually, so that's why I'm doing this for loop thing. So you can just say for call, or basically for column in df dot columns. So this would iterate over this column. So if you just print this column, right, so this would print all the columns that you have in your data frame. So this is how you can individually get the column names of a data frame using a for loop. So using this column name that we are getting from this for loop, I'm going to perform unique values. So I'm just going to say, uh, let's say columns to avoid, or I can just say numerical columns, numerical features. Let's call this as numerical features is equal to, we know that id, so id is actually not a feature, but we don't want to include that, so I'll put this in this numerical features thing. And the other one is like age, right? Because I'm not sure if this a1 score is binary or it also has like some values beyond 0 and 1, so we have to verify that. So but for age and result, we of course know that these are like values. We could see that in this data type as well, result and the age were float values. So here I'll say age and result. So age and result. So I can say if call not in numerical values, print column comma df column dot unique. And I'm also going to print some dotted lines that would separate those results, so it would make sense. So when I say hyphen asterisk 50, that's going to print like 50 hyphen, that would look like a dotted line. So basically what we are doing here is we are iterating over the different column names that we have, and those column names shouldn't belong to id, age, and result, because for sure we know that these are going to be numerical values. There is no harm in checking for these columns as well, but as we know this already, I'm just like skipping that. If you want, you can also verify this for these columns as well. Okay, so we have this numerical features over here, and then we are saying if column, if the column name, that means if it's A1 score, it's not present in this numerical feature, then it's going to print the unique values in this column. First print the column name, and then give the unique values there, and then print a dotted line. So after each result, you would see a dotted line. Okay. So first we have a A1 score. First ID is the value that column would take, but as this is present in this numerical features, this if condition is not satisfied, so this two lines won't run. So this id column will be skipped, and the next column is a1 score. So a1 score is not present in this numerical feature, so this two lines would run. So we are printing this a1 score using this particular print statement, and df dot unique would give you the unique values. As you can see, from a1 to a10 all the values are 0 or 1. So it's of course it's a categorical feature with binary values. We don't have to encode this, so it seems like it's already encoded, right? It can be a yes or no question or any question that they have asked, but I mean that's maybe not important for us as we don't have other information about this. And then we have gender as only f and m, male and female values. But if you see this ethnicity, right, you have a question mark, so this is what I've called it as missing values. And then you have white European, Middle Eastern, some different values are there, and then we have this others. So this question mark is something that we need to handle for ethnicity. Jaundice, we only have yes or no, so no issues there. Then for autism, we also have yes or no. And then country of residence, we have Austria, India, United States, and so on. So there are like few issues like uh, Vietnam. So this thing should be replaced. This space should be replaced with without any space and so on. There are like few adjustments that we would do for this. And then we have used app before also is yes or no. Age description, maybe this is description, I don't know. So it says 18 and more, but this, as I said, all these are like multiple unique values, at least two unique values. But this column has only one unique value, and hence because of that this is not going to be helpful for us. As if there is a column and it only has one unique value, then it's not going to affect your result at all. So we would directly remove this particular column. So this is the main thing. So we can directly drop this id column and this age desc column, so we don't need that. And then relation, we have self, relative, parent, question mark is also there in this relative column, others, healthcare professional. So if you remember, this is nothing but who kind of wrote that particular test for that person. And then you have class asd, 0 means autism spectrum disorder is not there, 1 means asd is there. So for relation column also, we could keep this as self and convert all this relative, parent, healthcare professional, all these two others. So it may be a chance that if the person is not able to write the test themselves, it may also mean that there is a high chance that they have autism, or there could also be another chance that someone else has written the test, but there is a chance that that could be a reason. So we could just keep this as self, and other things, all these other things can be others, even this question mark can be others. So that's the other thing. And even in this ethnicity, if you see, we have two others. One is with uppercase O, and the other one is like lowercase o. So we have to pay close attention to all these small details so that we are able to kind of work on this correctly. Okay. So these are the main insights that we got. I mean, towards this end of this initial inspection that we are doing, so here I've marked this as initial inspection, right? Towards the end, let's also mark like what are all the different insights we got from it so that we can handle that later. So for now, I'm going to directly drop two columns, dropping ID and age description column. So I've discussed like what is the reason for doing this. I'll say df is equal to df dot drop columns is equal to ID and age DESE. So run this. So we are kind of creating the same variable name df and dropping the columns ID and age description. So now if you check the df shape, previously it had 22 columns, now it has only 20 columns because we have dropped it. And again run this df.edf2, so that's going to run the two rows that we have. Okay, so this is what we have. So we have ethnicity and all those values are there. So the next thing is, if you want to look at the column names, you can use the same df.columns that we have used in the for loop. So that would give you like all the names of this particular thing. So now let's uh, maybe directly work on this mm, country of residence things I told you, right? So this Vietnam is there, this American Samoa, so this thing is there, so we can replace this to United States as well. So it should be a part of that. So Vietnam, we can just like replace this with Vietnam. And the other thing is like, I think Hong Kong was given, so when I was looking at it earlier. So we have we have China somewhere. I'll maybe search for this. Right, so here you have China, but in the same time you add Hong Kong as well. So you can replace this Hong Kong to China as well, as that basically Hong Kong is present in China, right? So you could replace those small things. I'm not sure if I kind of like missed some things in this country. If you want, you can also spend some time to make sure that the you know country is like properly represented or not, or if we have some city names and so on, so you can like verify that as well. So let's do that particular processing. I mean, you can do that in data processing as well, but these are like very basic stuff that we can do earlier. So just like dropping this ID and age description column thing, so we can do this as well. So I'll say df of country of residence. So the spelling is also not mentioned correctly, so it's missing a U. I'll just use the same name. So I'm going to say df of country of residence dot unique, and that's going to give you the unique values. So for this, I'm going to create a mapping dictionary, and there is a space over here. So in order to replace this, you can use this df dot replace function, but before that, we can create a mapping. So I'll call this as define the mapping dictionary for country names. So in this, if you want to, alter some other country names or city names as well, you can use that as well. So I'll create this dictionary and call this as mapping. So this dictionary, we will later pass this to the df.replace function. So first I'll call this as Vietnam. Somewhere here. Okay. So Vietnam can be replaced with, this would work if we don't do this as well, but just to be sure, like we are able to see the names properly. So I'll just use this name correctly as Vietnam. And then we have this American Samoa, right? Something like that. It's over here. I'm going to replace this with United States. Probably it should belong to the same thing. I checked it, but you can verify that once as well. And we have United States, and the last thing that I'm going to replace is Hong Kong with China. So all those Hong Kong values will be replaced with China. just like the value that we have over here. Okay, so this is the mapping dictionary. So later what you can do is replace values the country column. So for this I'm going to say df of country of residence, df of country of residence, same thing, replace with mapping. So this is the code. So this replace basically takes in a dictionary as its value. This dictionary we are defining it in the previous step itself. Instead of mentioning it here, you can also directly mention this dictionary here, but just to keep your code better, I'm creating a different mapping dictionary and later using this here. So df country of residence. I'm not altering any other columns. I'm just working on this country of residence column and saying country of residence dot replace with this mapping dictionary. So run this. And now when you run this unique thing again, now you won't see this Vietnam with that space or those particular American Samoa or Hong Kong. So all those values will be replaced here. So this is the processing that we do. But again, if you see any other issues with this country column, you can definitely work on this. And this other thing that I wanted to show you is like this is a very important thing to note, whether there is a proper class distribution in the target column. If there is distribution imbalance in this other columns, then that's fine to an extent, but the target column is very important for us, right? So you can check the target class distribution. So for this, mention the target column. So the target column is class slash ASD, and run this value counts and put a parenthesis. So that's going to give you the number of values in this. So 0 has 639 values, whereas class 1 has only 169 values. So that is like a very huge, almost a 1 is to 5 or 1 is to 6 kind of a variation here. So that is like a huge imbalance. So the number of data points for people who doesn't have autism is more compared to people who have autism. So when you put this to a classification problem, the model won't be able to identify correctly. So it will always probably say that the person doesn't have autism. So this is a serious issue. So in order to address this, you can either do undersampling or you can do upper sampling and so on, or basically also called as oversampling. So in this case, we are going to perform oversampling using SMOT, the synthetic minority oversampling technique. That's why we have imported this SMOT thing, which we'll use later. But these are all the insights that we are getting. So maybe using or what we understood from this initial inspection. So I'll just create this uh, pixel and call this as insights. So these are the insights that we got from here, and you can always mention this so that the next time you're reading this, it's like clear to you. So the first thing that we were able to kind of identify is that we add some missing values in this ethnicity and relation column, which we will handle later, but it's something to remember. And then we saw that this age DSC column as only one unique value, so it is removed as it is not important for prediction. So we have removed that. So that's like the other insight, but we have also worked on it, so we have directly removed that. So it is removed as it is not important. Next is like fixed the country names is something that we did, and then we have also identified class imbalance in the target column. Okay, so these are some of the key things that we have identified. Yeah, so later we have to handle this missing values, the ethnicity. So the main things that we have are missing values in this ethnicity and other columns. So these two things we have fixed, and we have also identified class imbalance. So these two things are pending, which we probably would do in the next exploratory step or maybe in the data pre-processing step. So let's get there. But the next step that we do, so first is importing the dependencies, then we have loaded and understood the data, and the third step is exploratory data analysis, where we are going to analyze this data more and also draw some visualizations for this. So let's call this as exploratory data analysis, or this is also called as EDA, and run this. Okay. So in this EDA part, I mean, we already know the shape of this data set. So we know that it's 800 into 20. Just if you want, you can also print the column name so that you can work on it later just to easily access that instead of scrolling above and looking at it every time. And maybe the end as well to just like look at the data set, like how it's looking like. So these are like the very basic stuff. So now let's try to analyze that. So first thing that we do in a EDA is try to understand the descriptive statistical aspects. Let's say if you have numerical columns, you would want to understand how the mean is looking like, median is looking like, and it would also help you understand what's the distribution is, and whether you have any outliers or not. In our case, almost all the columns are categorical, right? So we have about 20 columns, and out of this, age is a numerical column and result is a numerical column. And apart from this, like, other columns are categorical, and then we have the target, which is also a class, of course, right? So these are the things. So in order to understand the descriptive statistics, you can run this df.describe. So that's going to give you quite some information. So df.describe and put your parenthesis, and now you would have your count, mean value, standard deviation, minimum value, 25th percentile, 50th percentile, 75th percentile, and maximum value. So you can ignore looking at this A1 score, A2 score, all the way up to A10, as these are like categories, and also class ESD is also category. And then you have this age and then the result column, right? So these would help you to understand the distribution. Even in this categorical columns, if the value is around the zero point 0.5, as we have 0 and 1 as the two values, right? So the minimum value is 0, maximum value as 1. So these are binary rows, sorry, binary columns. That means they have either 0 or 1. If the mean value is closer to 0.5, that means like there is almost even distribution of zeros and even distribution of 1. But in this case, if you look at it, right, so the mean is like, in this case it's 0.2. That means there are more number of zeros and less number of 1, as we know that this is the target column. So that's how we can look at this mean even for a categorical column and understand that. So if you see this, right, so for 0.39, that means like slightly a bit more on the number of zeros. And even in this case it's 0.3. That means like in A6 most of the values are zeros, and I mean some values are like 1 and so on. So that's one way to understand that. And then age, we have the mean value is 27, and 50th percentile will be your median, 24. So there is like a slight difference between the mean and median. So that means like the distribution is not normal, or it's not like a bell-shaped curve. So we also call this as uniform distribution. And then for result, we have the mean value as 8 and median value is 9.6, which is almost close, but it depends on the range as well. So it doesn't give us a lot of insights, but we can understand this from the plot that we would kind of work on later. So I'll create another text cell. So these are like the very basics, descriptive statistics that we are understanding. And here I'll create another text cell, and I'll call this as univariate analysis. So univariate analysis, like univariate means like one variable. So univariate analysis means that we are going to analyze each individual variables, so how the values are. And you also have this bivariate analysis, where you take like two columns or two variables in sense two features, and you would analyze that, just like a correlation heat map that would give you the relationship between two different columns, right? So let's start with univariate analysis of numerical columns, and then let's do univariate analysis of categorical columns. So I'm going to mention this as univariate analysis, and this is for numerical columns. Later, let's work on the categorical columns, and I'm going to mention the two columns. So you can put a hyphen space, so that would be represented as bullets after you run this. So one is age and the other one is result, right? So these are the two numerical columns that we have. So you can see this bullet points, right? So that's created by this hyphen that you have. So let's analyze that. And I'm going to draw some plots to mainly understand the distribution, also maybe basically a histogram plot to understand the distribution, and a box plot to detect outliers. So I'll write a comment here saying set the desired theme. So using cbond, I'm going to set the theme. Okay, so even you can open your Gemini quickly, and you can ask a prompt if you are not sure about it, or if you, let's say, don't understand a particular code, right? So you can just directly copy this and put it here and ask it to explain this, just like putting this in ChatGPT, so that it's basically easily accessible. So you can just like ask this, and it would give you the explanation over here. Sometimes it can be wrong, but it's like easy to quickly understand that. Okay, so let me close this. So if you want to work on this thing, right? So I'm going to set a theme using C bonds. I'll open this Gemini and ask set a theme for my plots using cbond. So it would set up this grid and other things. So you can use this sns.set theme, but let's just use Gemini to get that. So we have already imported cbond. So you have this sns.set theme, right? So I'll copy this and paste it over here. You can use this dark grid or white grid depending on like what's the color that you want. So let's see how this dark grid is looking like. If it's not good, let's move to white grid. It's basically it creates grids on your plots and it makes your plots look slightly better. So that's the thing. So if first we are going to build distribution plots, later we will build a box plot. So I'll put this as distribution plots using histograms basically. So I'll say this as histogram for age to understand the distribution. So I can say sns.histplot df of age kd is equal to true. Title is distribution of age. Okay. And yeah, this should be good. Let's run this. Okay. So we have sns.histplot. So we have this dark grid. Okay. So if I put this as white grid, let's see how this is changing. Right. So we don't have any colors, but when you add this dark grid, right? So it just like kind of puts this blue colored dark patterns behind this plot. So that's about this setting this theme. So if you don't use cbones or if you don't set the theme, you won't see this grids at all. So we have this histograms for this age column. So we have this values about after let's say 5 or something all the way up to 80, and you can see that it's a right skew. So right skew means you are kind of seeing a larger tail towards the right side. That means there can be some outliers towards this, and when your data is right skewed, that means your mean will be more than your median. In a normal distribution or uniform distribution, the two values are like very close to each other. If it's a perfect normal distribution, then your mean and median value are the same. You can also draw your mean and median value here. So for that, what you can do is include those values as well. So first we have, let's say, first we have drawn our distribution. So kd is equal to 2. Kd is the kernel density estimation that would just draw a smooth curve above this histograms to look at this distribution. This, if you remove this kd is equal to true, you won't see this curve. Now let's say that I want to display the mean and median as well. So first we need to calculate the mean and median for this age column. So for that you can just say age mean is equal to df of age dot mean. And similarly, you can calculate the median value like this. Okay, TF age median. So these are the age mean and median values. You can print the values if you want. Maybe I'll show you. Print mean age and median age. And then you can add vertical lines in the same plot to represent this mean and median. So I'll say add vertical lines for mean and median. So use plt dot ax axis vertical line, v line vertical line, axv line, age mean color red line, style double hyphen dashed. Okay, line with one. mm, okay, so I'm going to change this line style to something like this, uh, double hyphen. So here I'll just change this to hyphen within quotes, and line with, maybe let's just work with the default one, but I'm going to work with this label and I'm going to call this mean. You will understand what this means, just wait a minute. And here also you can change this label to median. Okay, so I'm doing is like on top of this graph, I'm drawing a line that would represent mean, that's red in color, and drawing a line that would represent median, that's green in color, with some different in line styles for these two things, and create a label called as mean and median. So this should be median, and you can say plt.legend, so that would create a legend and it would show you, and then just put your plt.show. Okay, right. So as I said, right, so this is a right skew data. That means your it's kind of right skewed, so we have some outliers over here. So because of that, your mean is affected by those outliers. So you are seeing that your mean value is greater than median, but usually median is not affected by outliers, as we would arrange the values and pick the central value as the median. So this is where your central value is. So this is how you can draw this, and this PLT legend is nothing but this mean and median that we are representing here, the legend of this graph. And EX vertical line red color is this one is this line is drawn by this particular line, this line, and your green color median is drawn by this line. So if you see it's a dashed line, that's because we have used this double hyphen, and it's a solid line because we have used this hyphen thing. So this is how you can do this. So if you, again, let's say if you don't understand this code, just copy and paste it to, let's say, ChatGPT, or here you have Gemini itself. So these are like basic code, so it shouldn't make any mistakes, but yeah, there is a chance that it can happen there. So yeah, so we can check this here as well, so it would give you the code. So if you don't understand anything, you can maybe directly put this over here and get an explanation. Here we have also printed the mean and median values as well. So similarly, let's do the same thing but for result column. The reason we are doing this is to identify again whether there would be outliers or not, and also make sure how the distribution is looking like. The reason we are looking at this distribution is here we are working with tree based models, so no issues there. But in the case of models like logistic regression, linear regression, and so on, these models expect the data to be to have a normal distribution or uniform distribution, so they don't work well with skewed data. So in that case we would perform standard scalar, but that's not required in the case of tree based model, so we won't perform standard scaling. So the reason we are looking at this is, one is to understand the outlays, and the other thing is to make sure that you do proper scaling. So in this case, scaling not required, as I said, because of the tree based model. But if you want to try this prediction with a logistic regression or a SVM or those kind of models, you definitely have to scale your data. So that's the other thing. So I'll copy this entire thing, and let's do this plot for result column. Name this as a result. Change this over here. Let's change this age as well to result. Result mean, result median. Same thing over here. Distribution of result. Okay, histogram for result. It's for result column KD true, distribution of result. Calculate mean and median. So these are fine. Okay, so this should be good. Let's run this. So we have mean value 8.5 and median value 9.6. So it's kind of left skew, but there's not that much skew, I would say. But there's, of course there is skew, and as we can see, because of this left skew, the mean value is lower. So if it's right skew, then your mean value will be towards your right more than your median. If it's a less left skew, in that case your mean value will be less than your median value. So this is the understanding, as we would have outliers over here. Okay, so these are the values that we have. In order to I mean, this is just to understand the distribution, so that when you're working with those linear models you can scale it. But for outliers also this gives an idea, but to get like more clear picture on the outliers, you can do two things. One is a box plot that would visually give you the outliers, and then you can also perform this IQR, interquartile range method, that would count and tell you like how many outliers are there in your columns. Again, this we would do only in the case of uh, numerical columns. For categorical columns, in order to do a similar thing, we can perform count plot. We will get there, but first let's work on the numerical columns. So the next step is creating a text cell, and I'm mentioning this as box plots for identifying outliers in the numerical columns. Okay, so box plot. So for box plot, I can say SNS dot box plot and pass your data as x is equal to df of age, and then you can say plt dot title, and title I'm going to say this as box plot for age, plt.x labels. I'm creating a x label and calling this as age, and finally you can say plt.show. So this would kind of give you the outlays over here. We are getting some error. Okay, it should be a dot. So this plt.show, this should work now. So we are seeing this plot. So we have this age in the x-axis, we have the age values, and we are seeing something over here, right? So these circles that's present represents your outliers. So how these outliers are determined is this line that you're seeing in between this box is your median or your 50th percentile value, and this line represents your Q1 or your 25th percentile, or you can also call this Q1 or quantile, first quantile. This is your third quantile or your Q3. So this 75th percentile. So you have your 25th percentile, 50th percentile, and 75th percentile, right? So this is also called as Q1. Median or 50th percentile is also called as Q2. This is your Q3. So you have this line as your Q1 or 25th percentile. This is your Q2 or 50th percentile. This is your Q3. So this Q3 minus Q1 gives your IQR or your interquartile range. So interquartile range is the what's the value that you are getting after Q3 minus Q1. 1.5 times of your interquartile range, and whatever comes after this or below this, that becomes your outliers. So 1.5 times into your interquartile range. So that's what this line represents. So whatever comes after that, the value greater than that would become your outliers. If the value is less than, again, 1.5 times of interquartile range, whatever comes less than that, so that also becomes your outliers. So the circles that you're seeing over here represents your outliers for age plot. So this is how you can use a box plot to count the number of outliers. I mean, this is just a visual representation, but using IQR, we can count the values as well. So, okay. Next is we can do the same thing. Here we can see that there is like some number of outlays. There's not several outlays, but of course there are some outlays over here. Similarly, let's do this box plot for result column. Okay, so mention this the same thing, just change this age to result. X label can be represented as result. So here we got a left skew, right, for result. So for age we had right skew, so that's why we had the outliers on this case. Whereas for result we have left skew, so the outliers should be in this particular range or towards your left side. So let's run this. Okay, so it seems like there's only one outliers. We will confirm this later, but yeah, so we don't have several outliers, but I mean, it's towards this right side. The distribution is towards this right, whereas it's towards this left. This is like major amount of data, as you can see over here. Major amount of data is towards left, but the skew is towards right. So that's why your plot is looking like this. But for result, major amount of data is towards right, and few of them are towards this left, right. So that's why you are seeing this distribution as well like this. So we almost, I think it's only one outlier, but we can verify that. But this is how you can visually check whether your data has any outliers or not. So now we can count the outliers using IQR method. So I'll say Q1 is equal to DFH quantile of 25th percentile IQR. Okay, this should be good. Let's call this as lower bound is equal to Q1 minus 1.5 times into IQR and Q3 plus 1.5 times into IQR. Outliers is equal to DF. So let's call this as age outliers. Okay, so this is basically just the same thing as I said, like IQR or the interquartile range into 1.5 times. Whatever comes above that or below that represents your outlay. So that's what we are representing. So Q1 is your 25th percentile for this age, Q3 is the 75th percentile for this age, and you're finding this IQR or the interquartile range by subtracting these two. So lower bound Q1 minus 1.5 times of IQR. So this represents the line that we have over here, and this upper bound Q3 plus 1.5 times of IQR represents this line that we have towards the right side, upper bound or the higher limit. And whatever comes below this lower bound, that would kind of come towards the left of this line, and the ones that come above this upper bound, so those are the values that comes kind of here. So those two things contribute your age outlays. So we are kind of filtering our data frame. So you are filtering these values that are less than your lower bound and the greater than upper bound, so that would constitute your outlays. So these outlays we are separating it into a different DF called as age outlays, right? And once you get this right, so you can also try and print this outlays, but I mean we don't have to do that, but just to look at the data frame, you can say age outliers. So these are the outlier values for age. Now if you want to check the length, just say print length of age outliers or just length outliers. So when I run this length of age outlays, I'm getting this value to be 39. So in total, we had about 800 values, but 39 is actually a very less number. But let's not do this as it is. We can replace this outliers with median. You should not replace it with mean because mean is affected by outliers, whereas median is not affected by outliers. So later in the maybe data pre-processing step, let's write some function to replace these outlier values with the median value, so that we can do. So similarly do the same thing for result, but it should have very lesser number of outliers, as we can see from this plot. So count the outliers using IQR. All the things are same except for the result column. So change this df of age to result as well, and here as well we need to change this with result, and age outlays should be changed to result outlays, and then you can print the result outlays here. Run this, and there's only one outlier. I mean, we can, again, it's not a big impact, but we can change this as well, so no harm in doing that. But yeah, so age outlays at about 39 outlays, and this has one outlays. So the main idea or goal is not to just work with this particular use case. So the idea is you understand all these steps, so when you are working on a different use case, let's say in a company or for your project, you should be able to do these same steps for that particular use case. So there, it may be slightly different, but understanding all these concepts should help you to replicate this for some other data set and some other use case. So that's the idea. So this is the outlier analysis that we did, and this is probably the result that we can understand from this univariate analysis of the numerical columns age and result. So there are like few steps on how you can handle the outlays. So one option is you can directly drop the rows that has outliers, but that's not often recommended because you could lose some good amount of rows that you have in your data. In this case, we know that there is a class imbalance, right? So what if the moment you drop this, you in turn you kind of drop the rows that has those lesser number of values. So here you add 0 and 1, right? Let me go there. Like we have 639 data points for 0 and one class 1 has 169 rows, right? So when you drop those 40 rows, what if we lose like 20-30 rows in the class 1? So already we have lesser number of data points here, but if we drop this, there is a chance that we could lose something over here. So it's not recommended most of the time just dropping this. So the other handling part is you can replace the values with mean or median. And there are cases where the reason for outliers can be due to human error, or when the data is recorded there are some errors. But in some cases the outliers actually make sense. There is a chance that these are valid values and not just some random outliers. In that cases we tend to keep those outliers. We don't have to kind of handle that. In this particular case we don't have that information if it's this valid outliers are like valid or not. Oftentimes we need the input from the SME or the subject matter expert. Let's say you're working on a healthcare related use case as this one, and we have this age. Sometimes the subject matter expert can say that there is a chance that people with this particular age can have autism or something like that, right? Or they can say that it's not possible, so these are outliers are made due to some error, so you can replace this with median values and so on. So the subject matter has to give that explanation in some cases, and based on their input you would kind of handle that. So the main takeaway is that you can drop this, and in some cases there is a chance that outliers are actually real world meaningful values. In those cases we don't handle it, we don't change it with median value, or we don't drop that. So that's something to remember. And the other thing is, again, the tree based models are prone to this outliers. So there are outliers, they are not that much kind of affected by those things, whereas if you have this linear models like logistic regression, lasso, or even this SVM, right? So these are affected by the presence of outliers, so that's something you need to keep in mind. So the model that you're kind of selecting also plays an important role on how you are kind of handling these outliers. So keep that in mind as well. So in this next step, we have completed the analysis for the numerical columns. Now let's work on univariate analysis of categorical columns or the categorical features. Okay. So I'm going to select the categorical features from this. I'll just say df.columns. Again, we are going to do this distribution plot, but for as these are categories, instead of using histogram plot, we will be using the count plot. So that would be a good option. So I'll create a list and call this as categorical columns. one second. Okay, categorical column. So this is a list, and in this list I'm going to copy the value. So we know that A1 to A10 is categorical, age is not categorical. Maybe I'll just copy all these things except for this class ASD. Target class, maybe we can look at it later in a count plot, but in this case age is not a category, so I'll just remove that thing. And your result is not also a category, so you can remove this one as well. Okay, so the other things are categorical columns. So now instead of creating a plot like this for individual columns, I'm going to create a for loop that's going to do this. So I'll say for column or call in categorical columns plt dot figure. So you can just just say sns dot count plot. Within that, say x is equal to df of column count plot for this column. We don't need this particular thing. So we have x label and y label. Okay, let's understand what we are doing this. So I'm iterating this for loop within this list. So then the for loop runs for the first time. Call takes the value a1 score, and we pass this sms dot count plot xdf of call. Xdf of call is nothing but xdf of a1 score for this first time, xdf of a2 score for the second time, and in each case we draw this plot and so on. So you kind of now look at this count plot for each of this uh, you know columns that we have. So it's running. Yeah, now it has executed. So now we are looking at the distribution. So in this case, count plot for A1 score. So it's like decent distribution in these two cases. And this is also like almost evenly distributed for A2 score. In this case, there is a slight class imbalance for this feature. There is also a slight imbalance. There is like a huge imbalance for A6 score. So this is what I've told you when I kind of looked at this describe, right? So where the value was towards 0.3, whereas the mean is like 0. I mean, on the thing, even just looking at the mean value, we know when the values are 0 and 1, but the mean is towards 0.3, that means more values are towards your 0. So that's what we are seeing in this case as well. There are like more number of zeros, so there is a class imbalance in like most of these things. And this is the ethnicity, where we have like different ethnicity. In some cases we have like very lesser number of data points for different ethnicity. You can also increase this x-axis of this plot to look at like all these names properly. And we have this jaundice, yes or no, autism present immediate family members, yes or no, and so on. So we have like the main thing to note here is like there are several categories, but some categories doesn't have that many different data points. There are like very less number of data points. So again, there are few ways to look at it, and how you are going to handle this. Sometimes you can leave this as it, especially when you are working with a tree based model, so it shouldn't be a big problem. But in some cases this would create an issue, and there is no thumb rule on what you have to do here. So it all depends on, first you just like leave it as such, leave this class imbalance on the feature as such, and then you train your model and try to see how the model is performing. And maybe in the next iteration you try to handle this balancing thing, try to see if by balancing this, if you are able to get a better prediction, better performance scores, like let's say your accuracy, precision, recall, or your cross validation score. It's kind of a repetition and iteration we have to decide. In this case I'm just going to leave it as such, and just work on it. But again, you can again spend some time and understand if this can be done differently. But for simplicity's sake, let's just leave it as such. We will handle the imbalance in the target column. That's very much important, that's necessary. But for the features I'm just going to leave it as such. But remember that there is a imbalance there, and we can try working on that as well. And finally, let's draw this count plot for the target column, that is class ASD. So I'll say count plot for target column. I mean, you could have included this in the previous case as well, but I wanted to do this particular for loop plot only for the features. So maybe we can mention this as class slash ASD, the target column. Just code is the same thing. So count plot x df class ASD count plot. Oh, okay. So count plot x df. Let me press tab. Count class ASD. So okay, this should be good. And we know that there is a class imbalance. We have about 161 rows for class 1, and more than 6 30 or something like that, 650 for class 0. So of course there is a class imbalance and we have to work on it. So if you want to look at it better, you can also use this value counts as well. So say df class esd dot value counts, and that would give you the balances thing. So 161 and 639 is the distribution that we have over here. So the next thing that we are going to do in this exploratory data analysis, or your what we can say in our EDA, is your correlation heat map that would give you the relationship between two different columns. So before that, I want to do some processing on this data frame. So again, you can draw your correlation heat map now itself, but the problem is we have some categorical features, and you have some question marks and so on, right? So those would kind of create some issues. So what I'm going to do is I'm going to apply label encoder for the categorical columns and also handle these question marks, because I don't want to replace this question mark with a different label. So first let's handle this question marks that we have in certain columns, and then we will apply label encoder for the categorical features, and then we can draw our correlation heat map. So usually this label encoding is done in the data pre-processing, but just because I want to look at this correlation heat map, I just want to do this slightly before. So that's the idea. So now I'm going to handle this. We know that I think we have mentioned this in the insights, right? So we have missing values in ethnicity and relation in the form of question marks. Let's see how we can handle that. So I'll scroll down. Let me just check if the video is recording. Okay, right. So I'll create a text cell and say handle missing values in ethnicity and relation column. Okay. So what I'm going to do is in this ethnicity equal to same df dot ethnicity, we can't use fill NA because they are not present as NaN or not available or just null values. They are present as question marks. And I've already explained this to you that if you look at these unique values that we have printed, right, somewhere here. hmm, in this ethnicity we have two others, one others is with uppercase one, the other one is like with lowercase 4. We have to combine this to a single others, and we have to replace, we can just replace this question mark with others as well, because we don't know what it is. So let's replace this question marks with other. And relation as well, let's keep this as two things, self and others. You can put all this relative parent healthcare professional to others and question mark to others as well. I mean, we don't know if it's a right thing to do, but it's just one way of handling it. Again, you can do this in iterative process and try different things and which works better. But the logic is we are going to put self in one case and all these other things in others. It's again a decision that's kind of subjective. It's not like this is the only right way to do. So I cannot say that. It's kind of subjective and you can handle it differently. If that's working well, maybe that would be a better option. So you cannot say that this is right or wrong in this case. So I'm going to say df.ethnicity.replace. As I said, for this I'm going to create a dictionary, and we have to handle this like in a few way. So I'll say first is replacing this question mark. So put your key over here, and it should be replaced with others with uppercase O. Let's say let's remove this extra quotes, put a comma, and the other thing is this others with lowercase o should also be replaced with this uppercase o. So basically what we are doing is these are the two things that we want to replace. Oh, I think there is two dictionaries that was created. Okay, so we shouldn't have two curly braces. So this is the thing that we are replacing. All the values in this ethnicity column that has question mark will be replaced with the string value others with uppercase o, and all the values with lowercase o will be converted to this others thing. Let's run this. Similarly, for relation column, so you have df of relation, right? If you want to look at this unique values, just say df relation uh, dot unique. So that's going to give you the unique values. Now we can replace all these values now. So I'll say df relation is equal to df relation dot replace And maybe you can come to the next line and also create this dictionary as well so that it's easily readable. So first we can replace this question marks with others. uh, Put your question mark, so it's within quotes, say again within this, say others, put a comma, come to the next line, and here you can say relative, all these things with others. So relative colon others. I'll just copy this and maybe repeat this again a few times and then replace this parent then with others. So question mark should be replaced with others, relative is replaced with others, everything other than self should be replaced with others. So and parent is replaced with others and others is already there, and then healthcare professional. So these represents the person who wrote the test for that particular patient. So that's the meaning of this. So the curly braces. Okay, so this is what we are doing in this relation column. We are replacing everything apart from this self to this others thing and run this. So now look at the unique values of ethnicity and relation. So first I'll put in this ethnicity over here. So it should have, yeah, now it doesn't have that question mark and two others are not there, only one others is there. And then similarly for ethnic relation, you again can check this. Now you have only self and others. So these are the basic processing that we do. So now if you look at this df.add, this is the thing that you're seeing. So we don't have missing values anymore. So we have handled that. Later we will handle the outliers as well. But before checking this correlation matrix, instead of passing this as these values, I want to check the correlation here as well. So I'm going to draw this correlation heat map. Correlation heat map also doesn't give you much idea when the categories or nominal categories. Ordinal categories is when the categories has some orders in it. Nominal is one, the categories are like unique. So if you think about this ethnicity, we don't have any inherent order, right? But there are some categories that has order. If you think about movie review, right? So it says good, bad, worst. So there is an inherent order there. So that's called as an ordinal categories. And the other one is nominal categories when there is no inherent order there. And nominal categories doesn't, we don't have to look at it in a correlation heat map, but anyway, let's just perform this label encoding and then kind of draw this correlation heat map. So before that, we need to perform this label encoding. So and again, as I said earlier, usually label encoding is done in the data pre-processing step, but it's okay, we can do this here as well. Okay. So this should be done on the test data set, not just on training data and then do on test data. So that should not be done because you need this common encoding part for this entire data set. So you don't have to worry about leakage for this particular case. You can do this on the entire data set. So in this case, I'm not going to do this thing separately for all these columns. Like I'm not going to do this label encoding separately for gender, separately for ethnicity. Instead, I'm going to do a for loop and apply label encoding for all these columns. So and the thing is, like, you can perform label encoding for individual columns, and I'm going to save this label encoding columns as well. Maybe I'll complete it and I'll explain you. So first thing is we need to identify the columns that have string values in it. The way that you can identify that is check the data type. So wherever we have these categorical columns with string, those are represented as data type object, right? So we have ethnicity, jaundice, autism, and so on. All these are objects. So extract object data type columns alone and then apply label encoding. Okay. So here I'm going to say identify columns with object data type. Okay. So that can be done by saying object columns is equal to df dot select d types or select data types include object dot columns. So run this. And when you print this thing, you would see something like this. The columns that has object as data type in this. So you have gender, ethnicity, genres, basically all those categorical columns that have string in this name. So you can usually easily select this data types in this way by mentioning what's the data type that you're looking for. So here I'm looking for object column. So now I'm going to say encoders is equal to parenthesis initialize a dictionary to store the encoders and then apply label encoding and store the encoders. I'll explain you what we are doing here in a minute. So I'll say for column in object columns. Okay, so for column in object columns, label encoder is equal to, so we have already imported label encoder, so we can use that. So it should be with uppercase L label encoder and say df of column is equal to label encoder fit transform df of column and encoders of column is equal to label encoder. So this is for saving the encoder for this column and then save the encoders as a pickle file with open label encoders.pkl wbsf pickle dump encoder safe. Let's run this. So let's understand this code, but before that, let's understand the purpose or what we are basically doing here. So the idea is to perform label encoder, but also save these encoders because when you test this for a new data point that is not processed this way, you need to save this label encoders for later so that this transformation can be applied on the that unknown data set. So now we have this training data and test data. What if you want to test this on the data set that's outside of this entire data set that you're going to split? So this is the reason we save this label encoder. This is just similar to saving your standard scaler or your feature scaling aspects as pickle file. So we would save a standard scaler as pickle file, right? So similarly, we are saving these encoders as pickle file as well. So the other way would be to put all these things in a pipeline so that you can save that entire thing. But we can discuss about pipelines in a different video. But the idea here is like I'm applying this individual label encoder for this individual column. So there will be a separate label encoder for gender, separate encoder for ethnicity, jaundice, and so on. So all these are stored in this dictionary called as encoders. And after performing this rights, I'm saving this dictionary as a pickle file. So later you can extract this pickle file, extract all those encoders in a dictionary, later use this to transform the test data's columns that has like all these feature or all these categories, and that would be performed. So that's the idea. So you are performing label encoder, but you are saving that so that you can use it later in your predictive system code when you want to predict the class for new data points. So how we are doing that is, so first we have identified the columns that has object data type or basically has the strings as values in it. And then once we have this in the uh, for loop, we are iterating it over this object column or this particular list of column names and saying each time we are creating an instance of this label encoder specific for that particular column, and we are performing. So when the for loop runs for the first time, column takes the value gender, we create a new label encoder and say df of column. Df of column is nothing but df of gender for the first time. So say label encoder fit transform df of gender. So this df of gender column is updated to perform label encoding. So this male and female would be transformed to 0 and 1. And then you have this encoders dot columns, right? This is the data frame and this encoders is nothing but your dictionary. So you're storing this label encoder within this encoders dictionary with the key as the column name. I'll show you in a minute, but that's the idea. So at each iteration of for loop, you're applying label encoder on a column and saving that encoder to a dictionary with the key as the column name and then storing this entire dictionary. So that's the idea. So if you open this file, so you would see this encoders.pkl, which you can maybe download and use it for later, just like your model.pickle file. So that's the process. And here, maybe I'll show you this encoders dictionary. So you have this gender label encoder, right? So this label encoder is specific for gender, and this label encoder is specific for ethnicity. So later, when you perform this transformation on the test data, you need to access this dictionary, access the label encoder for gender, and apply that for the gender column of your test data, and then access label encoder for ethnicity, and then apply that, so that you know that how you have to replace others in ethnicity, and we also have others in relation, right? So how you would change the others in that particular column. So that's the idea. So this is kind of useful for you when you're working on the predictive system code. As I said at the start of this video, I won't be giving you that predictive system. I want to give you kind of this particular task of working on this one. So see how you could use these multiple encoders and then try to apply this label encoding on your test data and make a prediction out of it. So I just want to give that to you. So here we have successfully performed the label encoding. If I perform this df.8, again now all these values are now converted into categorical string values into numerical values. So it's like kind of generous transformed into 0 and 1. So if you look at this, right? So f is what we are having here. So it says 0 1 1 0. So your female has been transformed to 0, and the letter m has been transformed to 1, and so on. So this is scattered for ethnicity. We have different labels. 5 represent one label, 9 represent other label, and so on. You may think about performing this one-not encoding. No issues there as well. Again, label encoding is sufficient for tree-based model, but one-not encoding are better. But the issue is that it would kind of increase the dimensionality of your data frame. So now you would end up with like even more number of columns. So now we have 20 columns. Now when you perform one-not encoding, the number is going to increase. So that's something to keep in your mind, but you can definitely try one-not encoding as well. So here we have performed a simple label encoding that would convert the categories into 0, 1, 2, and so on. And in the next step, I'm going to draw my correlation heat map. So this can also be called as bivariate analysis, where you kind of look at two variables and understand the relationship between them. Previously, the univariate analysis, we understood the distribution of each of these variables. This is the bivariate analysis thing, and the correlation heat map is specifically useful for feature selection, where you can remove the highly correlated features, high positive correlation or high negative correlation. You can remove that feature because that would lead to multi-collinearity. So that's the other thing. So I can say this as correlation matrix or heat map that we would build. So I'll say plt.figure fixed size. So that's going to give my figure size. So sns.heatmap. So cbots.heatmap df.core would calculate the correlation heat map. Annotations to color map as cool warm, and the number of decimal values that I'm going to have is, let's say, two decimal values. So I'll call this as dot 2f. So that would give you two decimal values. Plt.title correlation heat map. Okay, and plt dot show. So this would draw the correlation heat map for you. You can increase the size. So it's kind of like congested. So maybe I'll increase this x-axis size and y-axis size to maybe 15 and 15. So the values would range from -1 to +1. So all those values you can see from this vertical bar in the right side. So +1 means like high positive correlation. That means like when one value increases, the other value also increases by that same factor. And -1, so it kind of moves in the opposite direction. So whenever you're seeing values with high positive correlation or high negative correlation, so though that means like two variables are highly correlated, so you would drop those values. So you would see like dark colored boxes, so that would mean like there is high correlation or high negative or positive correlation. In this case, we don't seem to have those dark values. You can ignore this diagonal because that basically means the same columns. If you look at this first box, right, so it's kind of the comparison between a1 score. This box is again a1 score, right? So that's why you have this diagonal thing. So you have to ignore this diagonal. So in this case, you take the column names in the x-axis and the same columns in the y-axis and x-axis in the both case, and just like try to find the correlation between those two columns. Okay, so as we have seen, we don't have any outliers when we kind of compare this, columns with the other columns. So if you just take this particular column, right, second value, the 0.40, this is nothing but the correlation for A1 score, if you just come down in the vertical line, it's A2 score. So it's like the correlation between these two things. So there is a 0.40 correlation. So there's no, I correlation, I positive or negative correlation. So that's how you have to look at all these other boxes. So as we don't have any highly correlated columns, we don't have to drop any columns and so on. So this is the insight that we are getting over here. So these are the EDA that we did, and we kind of got quite some insights, and we can maybe take a note of this. So some of the insights that we got from this, so based on that, we need to kind of process our data like that in the data pre-processing steps. So let's see what we can do with that. Mm, so I'll call this as insights from EDA. Check the sound. Sometimes I'm facing this issue of not recording the audio. Okay, so these are the insights from EDA. And the first thing is we saw that there are few outliers in the numerical columns. Numerical columns are basically numerical features, not the categorical one. Numerical features such as age and results. Results we don't have several, but it's just like only one outlier, but we can just mention that here as well. And then we have also seen that there is a class imbalance in the target column. I mean, there is class imbalance in the other categorical features as well, but we are not going to worry about that. So maybe we can mention that here as well, so you can work on it later when you get some time. So you can say that there is a class imbalance in the categorical features as well. So see if you could work on it a bit. And then I'll say that we don't have any highly correlated columns, so we didn't drop any columns for that particular condition. And the other thing that we did is performed label encoding and save the encoders. I mean, you could have done that in the data pre-processing steps as well, no issues. So these are the things. So first we kind of worked on the data understanding part, and then we did EDA. Now the next thing that we are going to do is data pre-processing. So this is the fourth step. So fourth step is data pre-processing. Sorry. So let's see what are the things that we need to do here. Uh, First is like we have identified some outliers. So let's work on replacing the outliers with median value. And then we have to, I mean, we don't have to perform this feature scaling as we are working with tree based models. So if we are working with logistic or other models, we would also perform feature scaling after train test split, so that we are not facing any data leakage. And the other thing is performing smooth. So we know that there is a class imbalance, right? So that should be handled, and the smooth is also performed after splitting the data into training data and test data. So first let's start with balancing, sorry, first let's start with handling the outlays. So I'll create a text cell and say this as handle the outlays, or maybe handling the outlays. Okay, so here I'm going to create or write a function to replace the outliers with median value. So I'm going to create this as a function so that we can use it for some other columns as well. So this is kind of a good template if you want to use this for some other use case. So that's the reason I want to put this in a function. So I'll call this as define replace outliers with median. I mean, this can be with median or mean. So I'll call this as with the median df of column. So first you need to pass a data frame and then mention the column name to which you need to perform this replacement. So and then I have to say q1 is equal to df column quantil 0.25. So that's right. IQR is also right. Okay. And then define lower bounds and the upper bound. Lower bound q1 1.5, q3 plus 1.5. So this is the lower bound is what's below this thing, and upper bound is this one, df of column. And then we have to calculate this median, right? So I'll say that median is equal to df of column median. That median value is stored there. Now we would replace that. So the next step, replace outliers with median value for those particular columns that we are passing here. Median value. So for this, I'm going to say df of column. There are several ways in which you can perform this. I'm going to use this lambda method. So I'll say df column dot apply, and then say lambda x colon median if x is less than lower bound, or x is greater than upper bound, L6. Okay, let's try to understand this, and finally you can return df. Okay, so the input of this particular function is going to be the data frame in which you are going to perform this change. So we are going to directly change this data frame, and you also have to pass the column in which you need to perform this replacement of this outlays. Okay, so we take this df and the column name as well. In this case, the two columns, we would do this one by one. First we would do this for each column. Let's say that we are passing the entire data frame and the age column. So we find this q1 for each column. So we have passed this age column here. So df of column of quantile 2.5 and then 7.5, finding the interquartile range, everything that we have did before, and then finding the lower bound and the upper bound to identify the outlays. Now calculate the median for this age column. So you are saying df of column, that means df of age dot median. So you got your age median value here and replace the values. And here you are not affecting any other columns because we are always addressing this df with the column that we are passing, where in this case it's going to be age, later it will be result. So think about this as df of age is equal to df of age dot apply lambda x. So what we are doing here is using this lambda function to say that when the x value is nothing but individual values, basically all the row values of each column. So this particular operation is performed for all the values in the age column. So whenever the age value, this x value is lower than lower bound, it's an outlier, right? And when it is greater than this upper bound, these two are the condition to identify the outliers. Lower than lower bound or higher than your upper bound, your outliers. So whenever this condition is satisfied, replace that x value with median. Else, if the value is within this particular range, then use x as well. So what this means is, whenever a particular row value or the age value is greater than upper bound or less than lower bound, then replace it with median value. If not, just use that same x value. So that's what we are using by using this apply lambda, and then we are returning this entire df. So you can call this by saying, so you can say replace outliers in the age column, saying that df is equal to replace outliers with median df of age. So here, as you can see, we are passing this data frame and then age. This returns a df that's again stored in this df thing. You can also create a new variable name as well, like it shouldn't be an issue. And that would be done. And then in the next step, we are doing the same thing for result. Again, we don't have to do this for result, but anyway, let's do this as there's just only one outlier. So, but anyway, let's do this. Replace outliers with median. If you want to replace it with mean, you can just change this median to mean, but we don't replace outliers with mean as mean is sensitive to outliers. So I'll just run this. So this should replace all those outliers with like mean value. Okay, just running the head and so on, and kind of finally checking this shape. So we have like all these numerical values, we don't have any categorical values, strings here. Okay, so that's the other thing. All right, so the next thing is, uh, let's split our data set into x and y, and then we would split it into training data, test data. After splitting the data into training and test data only, you have to perform this mode or this oversampling technique. So I'll say this as create a text cell, and maybe let's call this as train test bed, which is part of this data pre-processing step, right? So I'll call this as train test bed, make this bold, and say first df dot columns to identify the column so that we can represent this in x and y. So x should have all the columns. So we have already dropped id column, so we're not going to drop this again. Whereas in the case of x, I'm dropping this target column class asd. So x becomes your features and y, this uppercase x represents all your features and y represents your target column. Lowercase y represents your target column, that is class of asd or this autism spectrum disorder that you have. So okay, so we have x and y. I'll run this, so you can also print and see this x and y if you want, so that's okay. So we have all the features and so on, and you can also print your y to look at it. So lowercase y. Again, you can use uppercase y, but this is the general convention that we use. So now I'll perform this train test split by saying x train comma y train. Sorry, it should be x train comma x test, and then it should be y train comma y test is equal to train test split, and within that pass your x comma y, test size 0.2, random state 42. So just remove this reference thing. Okay, so X train is your training data features and the corresponding labels are stored in your Y train. Test data, the X test is your test data features and those corresponding test data labels are stored in your Y test. So you're using this train test split that we have imported from scikit-learn.model selection, and then you're passing your X and Y. Test size 0.2 means 20% of data becomes your test set and the remaining 80% is your training set. And random state is equal to 42. This is just for reproducibility. So when you use random state is equal to 42, you and I will have the same split in our X train and X tracer, like all those four arrays. So I'll run this. Now you can check the training data, number of values in your training data by running this print xtrain.shape, or even you can use ytrain.shape. Similarly, you can do this for your xtest.shape. So your training data as, sorry, it should be dot. So test training data is 640 and test data is 160. So 20% and 80%. Now we have to look at the distribution of how it's looking like for Y train and Y test. So if I check this Y train dot value counts, you don't have to mention the column name because Y only has like one column. So you can directly say Y train of value count. So that would give you the distribution as 515 for class 0 and 125 for class 1. So we can see that there is a clear class imbalance. Similarly, it would be imbalance in the case of test data as well, but we don't have to worry about that as we would perform this mode only on the training data. Later we would split that. So Y test is your value count. So 124 and 136. There is a imbalance in the test data as well. So we are not going to touch this as this is the final data set on which we'd be predicting our values and run the evaluation metrics. So here the next part is like how we are going to fix the class imbalance in the training data that we see over here, this 515 and 125. So we cannot train our model with this imbalance, this much imbalance. So create a text cell and call this as mode. So this mode stands for synthetic minority oversampling technique. Okay, so this is the full form for SMOT. So it's basically a simple oversampling technique. So SMOT also, I think we have imported from this IMB learn, right? So I don't remember that exactly. So if I scroll to the top, we have done so many things. Okay, so from IMB learn dot oversampling, we have imported SMOT. So this is what we are going to use later. So we are creating an instance of this SMOT. So say SMOT of random state, so that again this is also for reproducibility. Random state is equal to 42, and then say x train smooth comma y train smooth is equal to smooth dot fit underscore resample fit resample x train y train. So basically I'm taking not the test data, I'm taking the training data and performing this oversampling. In the case of undersampling, what we do is you have 125 in the class 1, right? So you take 125 values in this class 0 as well, and now you have equal number of this. So that's what undersampling means. But in the case of oversampling, you would resample this such that you would have 515 values for class 0 and you also have 515 values in class 1 as well. So that's the reason. So this updated data is trained in this kind of oversample data is now saved in this exchange mode. The features are stored in this exchange mode and labels are stored in this, our target class are stored in this white range mode. So I'll run this. So now when you check this shape, right? So print white trains mode. So previously we had, one second. First let's check the shape, then we can check the distribution. So previously we had white range shape is 640, right? So now let's see how many values we have. Because of word sampling, we have 1030 values. And now let's check the value counts. So instead of shape, I'm going to replace this with value counts. So now it would have probably like equal distribution. So now we have 515 values and 515 values for both the classes. Now this data can be used in order to train our models, so that I mean now there is a balance of the classes. Now the model would be able to identify the difference between them. So these are the steps that we would do in a data pre-processing step. The next step is model training. So I'll call this as fifth step as model training. Let's make this as bold. So as I said earlier, when we were discussing about the workflow, we are not just going to train the model, but also perform model selection and hyperparameter tuning. Model selection in the sense like take multiple models and try to see which one works well. And hyperparameter tuning is like selecting which hyperparameter to use. But before performing all those things, let's just train this with the default parameter that comes with sklearn or like other libraries. As I said earlier, we will be working with three models, but again, you can include other models as well. Nothing wrong in that. But we are just going to work with these three tree-based models: decision tree classifier, random forest classifier, and XGBoost classifier from XGBoost. Okay. So first, let's just work with the random parameters, because in some cases, what happens is, right, the hyperparameter tuning may not give you significant increase in the performance. So you can just stay with the default model as well, but you can definitely try hyperparameter tuning. But let's first just try to train this with usual parameters. So for this, to automate this particular step, I'm going to say list of classifiers. So I'm going to put all these classifiers in a list. So I'll create a list called as models, and I'm creating a dictionary, and the key would be, let's say, a decision tree. This is the key, and the value would be the model that we have imported. So the model that we have imported for decision tree is decision tree classifier, and then we are getting this suggestion. So we have this random forest as random forest classifier from sklearn and XG classifier, XGBoost classifier. No? Yeah, XGBoost. And again, I'll use random state for reproducibility. Usually we use the number as 42. It's not a compulsion, you can use different number as well. So we have random state for all these things. So basically I'm creating a dictionary where we are kind of listing this thing. Maybe I'll call this as dictionary of classifiers, as the data type is dictionary. Okay, so we have this decision tree, random forest, XGBoost. So these are like instance of those individual models: decision tree classifier with random state, random forest classifier, and XGBoost classifiers. Now I'm not going to just uh, train it and test it with accuracy score, not just one accuracy score. Instead, I'm going to run a cross validation score so that the score is more reliable. I hope you know what cross validation is. I've made video on that. If you are not sure about this, just go to YouTube and search for Siddharthan cross validation. So that will kind of show you the cross validation video that I made on YouTube. So you can just watch that if you don't understand this concept. I can just give you a shorter explanation. So you can choose multiple folds. If you use 5 folds, right? So your entire data is split into 5 folds. One fold will be a test data in the first iteration. And in the next step, the test fold would change. Like let's say the first fold is the test set. In the next iteration, second fold will be the test set. Remaining four will be the training set. So at each iteration of this cross validation, at each fold, you would change your test set. So now you have accuracy score on 5 different iteration, and you understand that you're not getting the score for one fold, but it's kind of across this data set, and it's how it's performing. So this entire cross validation, we would do this on this X-train, SMOT, and Y-train that we have built. This test data would be like the final global test data set. So the model has not seen this yet, so we would keep this for last. When we find the best model, then we can test this with the test data. So here I'm going to say dictionary. You can do this individually as well, but in order to save time, I'm kind of automating this with a for loop. So I'll say dictionary to store the cross validation results. So let's call this as CV underscore scores. And cross val score we imported from, I think, model selection, so we can use that. CV score. So create an empty dictionary, and now we are going to perform 5 fold. That means we would split this data into 5 different folds. Cross validation for each model. So for each model, we are going to perform this cross validation. So I'll say for model name, comma model in model dot items scores is equal to, let's, yeah, include another print statement and call this as print f training. The f string, it's basically used to replace or replace a variable name with a string value. So put model name here, training model. This means like when random forest is training, it would print random forest. When decision tree is training, it would print training decision tree model with default parameters. Okay. And then scores is equal to cross-val score that we have already imported. So if I go to the top, we have imported cross-val score from, yeah, model selection along with the train test split. Okay. So you're passing your model. So cross-val score, the first value that we are passing is parameter we are passing is the model. And then X trains mode, Y trains mode, cross-val. This is the number of folds scoring, whether it's based on accuracy or some other parameters. And then you can say CV scores of model name is equal to scores, and then print your average. Print if model name cross validation cross validation accuracy. So the mean cross validation accuracy would be this, says something like np dot mean. So we are finding the average np dot mean of scores. And just you can put dot 2f, so that would include like two decimal values. And after that we can also print this 550 times this hyphen. Okay, let's understand this. Let's understand what we are doing here. Okay, so at each iteration, or basically the first time, I need to uh, train this decision tree classifier using this cross validation so that I get this five scores, and then I get the average of this five scores and give one cross validation result. Okay, so that's the idea. So when you run this models, right? So when you or basically print this models, you would have a dictionary that would have decision tree, and like this is the first key value pair. So the decision tree, these are the default parameters. So and next we have XT boost, random forest, and so on. So these are the values that we have, right? So when this for loop runs for the first time, we have initiated an empty dictionary. When it runs for the first time, when you say model comma model name comma model in model items, model name will take the key which is decision tree for the first iteration, and model will take this decision tree classifier. So when you say model dot items, it's going to iterate with two things. One is the key and the other one is the value from this key value pair. So the model name is the key, which is nothing but the model's name that we have given, and model is the actual model that we have created an instance of. Okay, so the for loop runs for the first time, and we print that training for the first time. We would say training decision tree with the default parameters, and then we calculate the cross-val score. So this is the place where the model is fitted with those five different folds, and the scores are calculated, and the five scores are saved in this list called as scores, and this is then saved in this dictionary called a CV scores. So this will also be saved as a key value pairs. So there will be a key called as decision tree because we are using the same model name that we have extracted from this model.items. So that same key is used for this CV scores, and that scores are saved there. When I print this, it would make more sense to you. I'll show this to you later. But once we save all these things, we print the average of all those five scores and print it. Let's run this. So first, as you can see, we first train the decision tree with default parameters. So the decision tree cross validation accuracy, that means average of five scores is 0.86, and for random forest cross validation it's 0.92, for XG boost it's 0.90. Actually, this is not just training data, this is kind of like the test data accuracy as well. So it's not just on this test data accuracy, so it's on the cross validation result, right? So it's on that test accuracy, so it's kind of reliable compared to just a accuracy score that you would work on. So yeah, I mean the scores are pretty decent. It's 86, 92, 90, and so on, and the highest accuracy that we are getting is for random forest. Anyway, we would do hyperparameter tuning for all these models, but we can see that this is the highest score that we are getting over here for cross validation. Again, as I said, this is for cross validation, not just for training accuracy, so it's like kind of reliable. And if I just print and show you this CV scores, right, this is how it would look like. So decision tree is the key that we have created in this particular line of code using this same model name that we extract from this models dictionary. And we have this array of five, scores. This is the first fold test accuracy, like next folds test accuracy, and so on. So this is for random forest, and then for XGBoost. So we can say that random forest gave like better performance, slightly better performance compared to all these other things. Okay. So out of this default parameters, we can say that random forest is performing well. So yeah, so these are not the training data accuracy, but the test folds accuracy for each of those cross validation for each of those models, and we see that this is performing well. In the next step, let's perform this hyperparameter tuning as well as model selection. So here for model selection, we will slightly do a manual approach, but again, this can be automated with some loops and pipelines as well. But maybe that we can do in a different video. Now let's focus on this hyperparameter tuning and model selection with randomized search CV. So I'll say that this is the sixth step of, again, we are not doing model evaluation separately. It's kind of done in this tuning as well, but let's try to do that on the global test set later. We'll call this model selection and hyperparameter tuning. So you can, as I said earlier, you can do grid search CV as well, but that's going to take a very long time. So you can perform randomized search CV that we have imported from, I think, model selection. So here I'll say initializing models in the same way that we have did before. So I'll call this as decision tree is equal to decision tree classifier, random forest, and XGBoost. So these are the three models that we are again creating an instance of. Previously, we put all these things together in a dictionary, but I'm now creating separate variables for separate models. And now next we create the hyperparameter grids. Again, I made a video, conceptual videos on I have grid search CV and randomized search CV in my machine learning course. Again, you can search for it in YouTube as well, so look into it if you don't understand this particular concepts clearly. So I'll call this randomized search CV. So, or yeah, so this is for randomized search CV, but this can be used for grid search as well. So I'll call this as param grid underscore dt, but dt, let's say, stands for decision tree, and this should be given in a dictionary. So there are like different hyperparameters. I'm just like choosing very few hyperparameters and very few set of values, but you can try more number of hyperparameters with several combinations as well. So I'm trying this criterion, max depth, minimum samples, minimum. Okay, I'll just go with this default one. And for minimum sample leaf, I can maybe use 1, 2, 4, and so on. Okay, again, as I said, you can include more hyperparameters and different values as well. So I'm just want to keep this slightly simple. So I just keep this Guinea and entropy as the two different criterion, and then we have max depth as we change this to some other values, 10, 20, 30. You need to understand this model in a detailed way in order to make more sense of like how you can change the values depending upon the data set or the use case. 2, 5, 10 is sufficient, and then we have 1 to 4. Okay, so param grid for decision tree, Guinean entropy 10, 20, 30, 50, and 70. Similarly, for next one is like this is for decision tree, and the next param grid that we are going to do is for RF, or basically a random forest. Again, create a dictionary, and here we again would do some hyperparameters such as n estimators, 100. We have to put this in quotes. So all these values should be present within a list, the different combination that we are going to take. So at a particular point of time, the criterion can take only one value. Max depth will take only one value. So we would try like these different combination in grid search and randomized search CV. So for n estimator, which basically represents the total number of trees that you would have in a random forest model. So I'll say 50, 100, 200, and let's have 500. So these are the different number of trees that we have. Make sure that you put a comma over here, and then we have max depth as another parameter. Let's say max depth is 10, 20, 30. Okay, this should be okay. 10, 20, and 30. And then minimum samples split 2, 5, 10, and minimum samples leaf is 1 to 4. These are applicable for random forest as well. And Finally, let's use the bootstrap hyperparameter. I mean, I've just got this from online, but you can try these different parameters as well. No specific reason on what's the exact values you should use and what you should use not and so on. So you have to do a bit of a research there. So you can just like try different values. So for parameter for RF, we have 50, 100, 200, 500, 10, 20, 30, 2, 5, 10, true or false. Okay. And for next one is for the XG boost regressor. I'm using an estimator, the same thing. 50, 100, 200, and 500 here as well. If it's overfitting, you can slightly reduce the n estimators and then alter a few of these values. Max depth is 3, 5, 7, okay, 10. So these are the three values. And let's say we have learning rate. Learning rate, let's use as 0 0.01, 0 0.1, 0 0.2, and 0 0.3. So this is the learning rate that I'm choosing. And then we have subsample. For that, I'm going to use. Again, it's not mandatory that you have to use these exact values. Try different values as well, but use applicable values. You can refer to it online as well. And finally, we have column sample by tree 0 0.5, 0 0.71. So these are like the usual values that you would use. Okay, so these are the combination that we are going to use. So again, these hyperparameter is done separately, and we are going to select like one specific model out of these things. Of course, you can try other models and other models hyperparameter as well. So we have param grid for decision tree, param grid for random forest classifier, and param grid for my XE boost classifier. Okay. Now we have to pass these models that we have instantiated along with this param grid to the randomized search CV, and that would kind of give you the best model for each of this case. So this is performing hyperparameter tuning for three tree-based models. Again, so I'm going to mention here that the below steps, not just this step, but the cells that we would do after this as well can be automated. But for now, let's not automate that, as this could kind of complicate things. Later, I'll just like try to write this in a form so that it's kind of simpler to identify the model. So I'll just mention here that the below steps can be automated by using a for loop or by using a pipeline, but let's not just complicate things for now. Okay, so perform randomized search. Randomized search CV means like cross validation. So yeah, CV for each model. So each model we would kind of perform this. So I'll call this as random search, random underscore search. First one is for decision tree, right? So let's call this as random search DT is equal to uh, randomized search CV, and then pass your decision tree that you have created. So estimator is equal to decision tree that we have instantiated here, and then param distribution is equal to param grid dt. Scoring is accuracy. Okay, n iter is like how many total number of you know uh, trials that you have to do. So when you put n iter is equal to 20, so each model would have like 20 combinations. Actual combinations will be like very large, but in randomized search you can say like how many random combinations that you want, but it will try to compensate or it try to pull from all these different distribution, not just like randomly picking, but it will try to have this values from different distribution, different combination. So it would be like uh, you don't have to worry about that some of the combination will be missed. Of course, grid search is like kind of a brute force search, so you would have like all the combination performed, but in order to save time we can do this randomized search, and when the data set is also more like this is like slightly better. Let's do this thing later. Fitting, let's maybe do this later. Okay, so we have random search dt, randomized search dt, estimator is decision tree, so the one that we have created here. And then we have param distributions as param grid dt, the parameter that we have mentioned here, the hyperparameters mentioned here. N iter, as I said, total number of iterations, like cross validation fold is 5, scoring based on accuracy. So your best model will be selected based on the accuracy on that final cross validation average score, and random state for reproducibility. And in the next step, I'm going to create random search for RF. Similar thing, the one that we have done over here, similar to that. So estimated random forest param grid distribution is the same thing. Other things can remain the same. So param grid should be param grid RF, DT, RF, and XGB representing the model. Uniter 20, CV, all the other things should remain the same. Next is a random search for XGB. Again, XG boost. Oh, okay. XGBoost is the library name, so I don't want to use the same name. So I'll call this as XGBoost classifier. Okay, let's copy this and use this in the estimator name. Right. So we have random search DT, random search RF, XCB. So all those randomized search results would be stored here. So this is just creating with parameters. So we haven't fitted it or we haven't performed the training yet. So that we would do in the next step. So we are saying that these are the models. These are the grid for each of these models, DT, RF, and XGB. And enter maximum number of iterations, CV5, and so on, and scoring accuracy, random state, and other details. So I'll run this. And now we are going to fit the model. So basically train and find the cross validation accuracy. So that can be done here. So fit the models. So say random search DT fit exchange mode. Again, this should be done on this mode thing that we have created. So first we are doing the hyperparameter tuning for decision tree, then for random forest XCBs. This may take some time. Again, as I said, everything is the same for grid search CV as well. You just have to change this, you know, randomized search to grid search CV when you're using that grid search thing. So apart from that, like everything is same. Okay. So let's wait for this. So randomized search DT destined tree is done. Now random forest is running. Then you see boost will run. We can start working on the other pieces of code as well. Okay. So here we can write some if statements. So this is what I said. Like it can be automated, but let's just like write some if condition to find which model has the best score. Get the model with best score. Okay, so here I'm going to create two things. Best model. First, let's uh, kind of initiate it with none, and best score. Oh, sorry, none. Okay, and let's say best score is equal to 0, and then I can say if. Okay, so all those models kind of trained. So here, if random search dt dot best score is greater than best score, then best model is equal to random search dt dot best estimator. Okay, and random sort best score will be this. I'll explain you after completing this code. And then if random search RF is the best score, then that should be the best model. XTB. Okay, let's try to understand this. This is like a simple if condition. And the thing that we are doing is like when you perform this right, your yes best estimator can be identified. Maybe I'll show this to you here. I'll print this best estimator and best score as well. So random search DT. And I put this dot best estimator underscore. This is the name for this attribute name. So decision tree of criterion entropy max depth 30 and random state 42. So this kind of gave you the best result. So that's like what it basically means. Again, all those parameters not mentioned here, but yeah, those combinations are considered. And if you want to understand the best score, you have to mention best score here. So this is the best score, that is 8.6 for decision tree, and for RF it just changes DT to RF, and that would give you the combination for this one. So we have max step 30, max step 20, n estimate is 50, and so on. So we have this particular thing for random forest thing. So yeah, bootstrap, max depth, n estimator, and random set. So similarly you have like all these things, right? So the different combinations of max depth of 20 and yeah, n samples that we have considered. So we need to identify which has the highest score. So for that we are kind of creating this if condition. So first we are saying that best model is none, best score is equal to none. So if the random search of DT, that means like if decision tree as the best score, that means this best model will be replaced by the best model of that DT's random search, and the best score is DT's random search best score. And then in the next we check if this best score that you got from the decision tree is greater than or less than randomized search of random forest classifier. So it's basically like first you update each step with the best score and the best estimator. First you check the best one in the decision tree, and then you compare it with the random forest. If random forest is the best model, then this best model and best score are replaced with this model's details. If it's not, then this decision trees values are retrained for best estimator and best score. Then you have XT boost for the final thing and so on, and this process goes on and so on. So these are the steps, and when you run this, you would kind of end up with the best model and the best score, and that can be printed. So now these two variables are kind of like updated, and you can say print uh, best model. And you have to say, so you can just use maybe a f statement, sorry, f string. So I'll say f of best model would be your best model variable, and then you can say best cross validation score or accuracy would be your best score colon dot 2f, that means like two decimal places. So here it would have print like what's the best string. So your random forest is the best classifier with bootstrap of false, max depth of 20, unestimated 50, random state of 42, and your best cross validation accuracy is like 0.93. So these are the things. Okay, 0.93. Again, for the default model we got 92, but we did all this hyperparameter tuning only for like 1% increase, which is like not that much of a improvement, but that's okay. We can definitely try, and in some cases it can give you like better performance as well. But this is what we are getting. So this is the best model, and this can be saved as a pickle file, and that can be used for later for your prediction. So I'll say this as saying, save the best model with open. Let's save this as best model.pkl. Put this within quotes, comma wb. So write this file pickle dump best model if. Okay, so this would create a pickle file and store this best model, and you can see this, and you can download this along with the encoders. So we have already created the pickle file for encoders, and here we are creating a pickle file for the best model that we have over here. And again, as a final step, you can test this on the evaluate on the global test data that we have splitted in the step before we have performed smooth. Yes, the one that has 12436, but this actually can give you accuracy would be good because of this class distribution, but you would eventually have like lower values either for this precision and recall because the distribution is less, right? So when the model is making wrong predictions for very few values of this class one, your I think recall of the precision, one of those will like drop very highly because of this lower values, but that's okay because we are getting like good values on the cross validation metrics. You can definitely work on improving that. If your test data is also giving you like very good precision and recall values, that means like your model is like kind of very accurate with the smooth that we did. But this is like, I would say this is okay because the cross validation results are like kind of reliable, and it was like about 90 percentage and so on. Again, this can be improved, but this is okay for now. You can also try to improve this thing. Before that, let's get the values. Yeah, I'll mention this as seventh as evaluation, model evaluation. This is a prediction that we are going to do. So prediction should of course come from the best model that we have, and say best model dot predict, and within that pass your x test, the test data thing before smooth, and print your classification report. Maybe, well, first let's print our accuracy. Here I'll replace this with accuracy score, And this, let's also print a confusion matrix because that would give you an idea of how much mistakes your model is performing for those two different classes. Let's call this as accuracy. Let's call this one as confusion matrix. And finally, we have the classification report over here. Okay, so we have the X test should be this thing. So your prediction, that is white test spread, should be compared with the true labels of white test, sorry, X test thing. So yeah, basically you're comparing your true labels and the predicted labels, and you're kind of giving the output. Let's see. So the accuracy is 81.8, but as I said, this is not reliable because there is a class imbalance thing. And in this confusion matrix, right? If you see this, maybe I'll print this without this confusion matrix because then we would have this matrix properly readable. Let's see. Or yeah, I think I can maybe put this in a new line, so that should be better. Okay, I think this should be better. So your accuracy score is almost like 82 percentage, but again that's not reliable because of this imbalance thing. So yeah, 108 is this 108 and 23 are the right prediction. This 13 and 16 are the wrong predictions. I mean, I can say it's like both the cases are similar wrong prediction, but the problem is as this has lesser number of values, the the precision for this particular thing has been like reduced. So that's the thing. This is what I was kind of mentioning you because the test data is not balanced, and because of that, you are going to get lower precision recall for one particular class. So that's what we are seeing here, and this is the average and so on. But again, you can of course try to work on improving this. Like if you're getting like high accuracy, that means like your model performed well on that smart data and the final global test data as well. But yeah, we could see that the cross validation accuracy is also good. The reason I'm saying that this is reliable is this is coming from the test data of the cross validation, so it's kind of like okay to rely on that a bit. I mean, there are some more sampling as well, but that's okay. So this is how you can work on a data set that has like class imbalance, but also we have worked on performing this hyperparameter tuning and model selection along with a lot of EDA and data processing of handling the outliers and so on. So these are the things that I wanted to discuss. As I said earlier, I wanted to give you some tasks that you can do. So maybe I'll just put this as to do. The first thing that I want to you to do is like build a predictive system out of this with encoders and the model file. So let's say that you have a new test data point that's not been labeled encoder and so on. So you would extract this encoder that has like several encoders, and then you would perform the label encoding for specific thing. So think about how you can do this. We just go above, right? We could see that encoders that we have saved somewhere. Yeah. So you have different encoders for different columns. So see how you could use that and then save these two things and try to build a predictive system. Maybe you can deploy this on a Streamlit app or a API and so on. So you can do that. We have already discussed about that. And next step is like try to see how you could, see if you could improve the performance. You can maybe work on, you know, uh, performing or basically do some better analysis. Try to see if you could find some relationship that we didn't do or we didn't pay attention to, or process the data better or perform like better feature selection and so on. So see like what are all the things that you can that can be done. Yeah, just I wanted to give those two things as an exercise. Later, as I said earlier in the previous video as well, I'll try to make videos on, let's say this is the accuracy that we are reaching and how to go from this point to the next point where you'd be able to, increase the performance, or basically increase the performance of your model accuracies and so on. So these are the things that we have discussed. Like it's kind of like an end-to-end, except for deployment, we have almost done like everything. So we have did detail EDA, data processing, model selection, hyperparameter tuning. So things can be better at model selection by automating that, but let's do that on different case. And I hope that you have learned whatever we have discussed today. I'll share the notebook in this video description. You can download this and work on it, but please try this out by yourself so that you get like a better understanding. And you can use this as a template for other use cases that you're working on. So that is all from my side, and I'll see you in the next episode. Thanks for watching.